So, welcome to my second lecture in this series, Introduction to Artificial Intelligence, the second lecture within the module about cognition. So this is a shorter video about the history of thought in cognition, so essentially of theories in cognition. And I focus on human cognition, but I will also make it part of the narrative to look at how ideas in artificial intelligence and ideas in human cognition, theoretical ideas, were interrelated. So cognition was of interest to the first psychologists. What's happening? So cognition was important to the very founders of psychology. Wilhelm Wundt is often credited with creating experimental psychology, and a lot of the questions they were asking were about decisions humans make and discriminations they're able to make and so on. And the theoretical perspective was called apperception by Wilhelm Wundt, and we would say the method was introspection, was sort of exploiting awareness of the kinds of processes that are taking place when participants solve these kind of tasks and behaved. This was a discipline that was just emerging at the time and had still very close ties with philosophy. William James thought very much about that. He has this notion of stream of consciousness that he analyzed and described in detail. He wrote the first very famous textbook on psychology in the 19th century. So there was a lot of important insight at the time, and some of the methods that were developed very early, especially psychophysics, Helmholtz, the Fechner's law, and Wilhelm Wundt himself also produced some such results. Those have survived, are still part of the repertoire of tools of experimental psychologists today. But especially the part about cognition and memory and the higher functions, that was increasingly troubled by essentially what was considered speculation, that there wasn't clear answers. It wasn't really a scientific approach. It was sometimes thought of as being a speculative approach where there wasn't a scientific procedure to agree on interpretations. A similar crisis was actually occurred in philosophy at the turn of the century, where analytical philosophy, which ultimately emerged from that, was trying to be more scientific. And so one sort of radical stream of that is positivism, where you emphasize very much experiment, measurement, observation, and essentially try to eliminate from discourse concepts that were not directly accessible to observational measurement methods and so on. So in psychology, this led to what's called behaviorism. In strict form, it really emphasized very much that you have to have observable, a concept needs to be observable, operationalizable through experimental procedures. So inner states that are unobservable would not be allowed in theoretical accounts. Essentially, behavior then was stimulus-response association. So you were able to operationalize stimuli, the paradigm, and then observe the behavior as a response, measure that, and behavior would be essentially just these associations that you observe. These would not be limited to only the fixed reflex-like stimulus-response associations or fixed action patterns that have been studied earlier in biology, Sharrington, and many others. The idea, the key technology was that the psychologists were looking at stimulus-response associations that could be modified by learning, and the learning would be structured by the experience, by the tasks, the environments that the animal or human would be exposed to. So conditioning, the classical Pavlovian conditioning, for instance, would be a paradigm, and instrumental conditioning, a development of that, where you were able to induce much more complex patterns was a very important tool. This was successful in the sense it led to important discoveries that are still around, still very important in psychology about animal learning, as it's called, including also humans, including human animals. Is today, for instance, under the label biological psychology, work of this nature. Actually, here at the Ruhr-University, we have a strong group in this field, headed by Professor Günther. And it's also still important in artificial intelligence, or let's say again important in artificial intelligence, through the notion of reinforcement learning, which is essentially the theoretical generalization of the instrumental conditioning kinds of ideas. And Professor Glasmachers will be lecturing about reinforcement learning from this machine learning, the modern perspective, mathematically framed, toward the end of the course. I think it's the second last lecture in this course. Now, this program of this dogma of no unobservable inner variable, those very strong limitations on research, and there it seems that it was almost like a sect-like situation where you couldn't, would be strongly criticized if you violated that dogma, and there was increasing resistance against this sort of sterilization of research, where a lot of questions were not accessible through this form. The most articulate, as far as I know, at least the left a good trace in the literature, were arguments about the need for inner state to understand language. And Chomsky was a famous spokesperson for this, what ended up being called the cognitive revolution, this counter-reaction to behaviorism. So, for instance, his own work in linguistics was, had this notion of universal grammar as a set of rules that operated on symbols. And you see, there's already the grain, certainly inner state, and you can see already the grain for computational. I'll come to that. He argued against behaviorism on the basis of what is called the poverty of the stimulus, that is arguing that the experience of a child with language couldn't possibly provide enough examples to uniquely determine these rules that universal grammar uncovered. And so children must have some innate machinery, that will be this inner machinery using inner variables that enables them then to learn language, because they already have so much pre-structure in there. Actually, that particular argument might now be, again, subject to some debate, but it was very important in freeing psychology of this corset of behaviorism. Once internal representations were admitted again to the theoretical repertoire of psychologists, enormous research productivity resulted. So it became a whole machine, research machine, you can almost say, that cognitive psychology, where you essentially you were always making measurements on these representations, now in this indirect sense that you were observing measures of performance, for instance, the time to provide an answer to a certain task, maybe the rate of errors, the type of errors, maybe something about the metric precision of the performance. So indirect measures of the postulated underlying representations, but by varying paradigms that invoke different hypothesized representations or different cognitive functions, experimentalists were able to tell apart a lot of different kinds of modules. Increasingly, they expanded this repertoire to neural measures, originally as neuropsychology, where you would see specific deficits in performance that could then be attributed to discrete different underlying representations or underlying cognitive functions. In more recent decades, observable techniques like imaging techniques and even transcranial magnetic resonance and other things were TMS, actually stimulation, sorry, transmagnetic stimulation, open up new avenues to provide experimental measures that can essentially always discriminate between different functions, with the logic that if it's different brain areas or regions that are engaged when you vary something in the task, then you could say that's a different function that's involved. This perspective is in psychology often called information processing perspective. In German, Informationsverarbeitung. That would be a very general concept, but it really refers to this more specific idea of computation. So thinking of cognition as a form of computation, sometimes called the computer metaphor, the brain functionally being equivalent to a computer. It would be manipulating symbols that are constrained by rules and so on, and I'll expand on that. So it's interesting that this conceptualization really was aligned with the beginnings of AI. So famous names like Herbert Simon and Al Newell, who actually developed sort of a research program. They had an agenda for how to systematically do that research, and these researchers were interested both in human cognition and in artificial intelligence, in the sense of creating, for instance, general intelligence in the system and an agent. Al Newell, for instance, was active in both areas, and in fact built a cognitive architecture that I'll come to next. One important idea was the idea of modularity, so that computational elements would be defined entirely by their input and output interfaces. Their inner state would not be penetrable, so not be accessible to other modules, and for instance, not accessible to awareness. Philosopher Fodor and psychologist Felician argued very vividly about that. There were debates later about to which extent that is actually really true. And you can perhaps see that this notion of impenetrable modules is related to the notion in artificial intelligence of encapsulation, that you have variables that are hidden to the outside. So very parallel development, and encapsulation is a standard technique now of computer science that came from artificial intelligence research, is not taken for granted. This modularity was important to theoreticians more so maybe than to experimentalists, because it implied that you could understand cognition by understanding how these different modules are linked, are interchanging their inputs and outputs in a cognitive architecture. And what is inside the module wouldn't matter. You could just find a description. I'll show you some examples of such descriptions for that. So some of the famous cognitive architectures were actually essentially programming languages in which you could write down such cognitive architecture. So for instance, SOAR, it's an acronym, stands for something I don't remember, was co-developed by Al Newell, whom I mentioned previously, was really in AI, and ACT-R was developed over decades by John Anderson. I wanted to say a few things about ACT-R. It's a little easier to characterize ACT-R. Originated in a model John Anderson published in the 80s about memory, where elements were standing for something, for the contents, the memory item. And that was in a sense symbolic. It was just like a computer variable stands for something. And these elements would have activation variables, so neurally inspired, that evolve in time and that can be passed on to other elements. It was a interactive activation model where they would these activation would determine what happens in the more advanced version. ACT-R, these elements are chunks that represent facts. So the facts can be memory items, but can also be perceived items, motor commands, or also rules and operations. And we'll come to that. And so that's the symbolic part where they stand for something. For instance, for now here an addition fact for some capacity to represent the state of an addition machine and adding machine. And associated with each chunk would be subsymbolic variables, which really means graded and time varying variables that are called activations, and weights that determine how strongly they can impact on other variables, on other chunks. And the notion would be that when a chunk fires when its activation variable goes above a threshold, and that would mean that whatever its content is now being realized, fires in analogy somehow to a neuron. And so the operation, for instance, if the chunk is an operation, it would be executed, like a subroutine would be called, and the addition would be performed, for instance. So here, so there was the thought that there would be a modular architecture like that. That would be a cognitive architecture that would have a procedural sort of engine, and that could have access to, for instance, visual information or imaging, things that you image and other kinds of sensory inputs, have access to motor systems, access to memory, and access to ultimately goals. That will be what programs this procedure. So here, for instance, an example where you would apply for mental arithmetic, you would have a goal of solving an equation, and you would give you some visual representation of the task. 3 + x is 8, and maybe a procedure subtract could be fired, and that leads to some other declarative representation and another task of subtracting and so on. So in fact, mental arithmetic was sort of the workhorse of a lot of these, certainly of vector. They always worked around particular example systems where you can actually perform experiments. The comparison to human cognition was based on a measure of performance, how much time they need to achieve certain sub-operations. And so here's an example of how that's done. For instance, there was a postulate from observation that children perform certain operations differently than adults. And one was able to frame the workflow when they do this operation in Act R and predict the times they need then for the different steps. And then as these times between the model and then the different infants versus adults line up, then that will be considered evidence for that computational principle being taking place in the minds of these children and these adults. These data, I mean, these sources of evidence are accepted. They fulfill certain criteria for modeling in terms of the number of parameters, limited number of parameters, many data points, and so on. Even though I would say that we can all see that it's not extraordinarily constraining. It's a sort of a weak constraint given the elaborate nature of these models. So today, I would say these kind of cognitive architectures still play a practical role in cognitive ergonomics when people assess, model the behavior of humans, for instance, in driving. People make driver models, about the cognitive load, for instance, that you suffer when you interact with different tools in your car, using models like that. And I would say there are models in higher cognition. I decided not to go into mathematical psychology. There is a sub-branch of this field that really uses very precise concepts for how to assess, empirically assess theoretical models. And I would say these architectures are still the backdrop for that kind of work. And in fact, they are being used to make rigorous interpretations of neural imaging data, because you can use certain techniques to map these modules onto brain areas. I say still here because I'll next talk about connectionism that criticized that view and that has certainly become dominant, I would say, in psychology. Yeah, and so that's the next revolution. You see, the history of thought is a sequence of moves and counter moves, which is sort of typical of psychology, that there's periods where paradigm dominates, and then sometimes a so-called paradigm shift in which some of what was previously postulated is actually refuted, and sometimes maybe too radically, and a new framework is erected. So connectionism arose essentially out of a criticism of this kind of approach. It's a complex story, but the core criticism was that the brain clearly isn't a computer. It doesn't have a CPU. It doesn't have random access memory. It cannot pass information along. So this is not the argument that its hardware isn't like a computer, which is also true. but it's that certain functional principles, the idea of passing information from a module to another, that isn't really possible in the brain, because it's always really just activation that's passed along. It's not clear how symbols would be represented and so on. So the notion was the brain is just a huge neural network, and all its functions emerge from the connectivity of that network. So this notion of brain-style computation arose. Connection was considered a revolution, although you could say the conceptual difference to information processing isn't as radical as it maybe first sounds. And you see this here in one of the oldest, this is from the original Connectionist Bible. Parallel distributed processing was like the summer school, and there were 3 volumes of a book that includes some software for that. That was very influential. A very early model. And just to illustrate a little bit the style of thinking, for instance, this is a model that links some grapheme elements like these line types, and then you could represent letters, and from that you represent words. And so the nodes stand for something, like these nodes stand for these words, and these stand for these letters, and these stand for these line elements, and the nodes pass activation among each other. The connectivity can be complex. You see, it's not categorically different from what I just showed in Act R, but we'll come to some important differences. But there is a certain continuity here too. And so rather than cognitive architectures, now you would have connectionist architectures that would ultimately have some link to, again, visual inputs, auditory inputs, maybe ultimately motor inputs. And it was also a similarity in that the way these networks would link to experiment would often be through processing time. So reaction time, how long does it take to solve the tasks, to access knowledge, to respond, and so on. And there would be predicting these times correctly as a function of the nature of the task would be considered to be results. And maybe I don't go into the details of that. So this started in the early 80s, as I just hinted, and a plethora of different kinds of models have since been studied from this perspective. This is from recent, or not so recent, from an older review of some of the founders of this field. So this goes from very simple networks, feed-forward networks with more or less complete connectivity, but also includes recurrent networks as these attractor networks, which are really dynamical systems, competitive networks that are actually can be implemented as attractor networks, and like Boltzmann machines, Hopfield nets. So some of you might know that, and you will encounter some of these later in the machine learning part when it's neural network based. I'll come back to that in a little while. So the important idea where really connectionism was quite different from information processing was this idea that you determine the parameters of these models from something that is called learning. And so on the one hand, that these are very many parameters because all the connectivities have to be specified, and it scales terribly. Combinatorially, if it was completely connected, there would be the connections in the real brain. If it was completely connected, would exceed the number of particles in the universe. You can see with the combinatorial explosion, there's a lot of space. These models are then constrained structurally to not be completely connected. So these many parameters would be determined in some kind of objective procedure. While in classical cognitive architectures, there would be an attempt to restrict the number of parameters to a smaller set so that they ultimately could be uniquely determined, which was sort of the holy grail of mathematical psychology. So here, there were many parameters, but their procedure would be obtained from a learning procedure, and that learning procedure was not really a learning process in the animal learning sense. It was essentially a fitting process or optimization process where you find the right parameter values in which the model performs right, that gives the right answer. And you do that on examples that you use to teach the network, and then test the network on new examples that it wasn't taught with. And if you show that generalization, then you say, I have captured something about the structure of the representation. So in a sense, a lot of these networks were also still computational, in the sense that there is an input and you're getting a response, and the training which you make use of examples of such responses for inputs to find the right connections. Now, these learning rules, especially the backpropagation rule that you'll encounter later in the course, were not argued to be neurally realistic or to really take place like that in humans. And in fact, the behavior itself wouldn't be natural behavior. It's not like you're learning by people showing you a lot of examples. But a strength of this approach was really that it would capture, to some extent, the structure of representations when the statistics of the examples that were shown really reflected properties of the world or of experience. And there were some interesting insights in that way, for instance, in the developmental literature of characterizing how children learn words and in which order and what kind of mistakes they make early, overgeneralization and so on. And those were plausibly linked to experience, to the statistical description of their experience, not their experience concretely modeled, because that was beyond these models, but to just described. And so that is, I would say, the remaining and the main strength of connectionist representations. So here's a just very crude example, not explained in detail. Models that learn concepts, for instance, that you would have a canary that has that can fly and sing and grow and move. I mentioned that in the previous lecture, about concepts being conjunctions of features, for instance, and by teaching a network properties of objects or categories with these different feature values, it would learn the distribution in these feature spaces. And one result of that could be that it would learn neighborhood relationships and similarities. And then you can look at how these this form of grouping reflects cognitive performance, like when people are asked how similar are different kinds of fish, and what is a typical fish, and what is a typical tree, and so on. Then they might the model might capture these kinds of that structure of the representation. So connectionism is essentially just a psychological part of machine learning when machine learning uses neural networks. So neural networks, connectionism uses neural networks, and it's nothing mathematically different. It's really just that the emphasis was on linking to human performance, while in machine learning, then neural networks were just used as a method of statistical learning. And you will have a lot of lectures about machine learning in the second part of the course, which will not emphasize so much the analogy to human cognition. Now, Lawrence Viscott last week showed you some special cases that are quite closely linked to the neural networks in the brain, and where that link, which you could call connections. I'll actually characterize that a little bit better in a moment. So I don't think you will be seeing much more connectionism in this sense of psychology, but you will be seeing that same mathematics in the second part of the course. Now, one more step toward really neural realism is sometimes called computational neuroscience. It's not very precisely defined, but it would be essentially connectionist models that are neuromechanistically more committed, more serious, really take into account neurophysics, like the membrane dynamics or synaptic dynamics, constraints like that. And there's a continuum of such models. I'll give you an example here, a model of working memory as sustained firing of neurons. So for instance, neurons that are stimulated by some input, then keep firing in an interval when the animal is supposed to wait before it gives a response, and how it can keep that firing is actually here, that the neuron keeps firing. How that can come about is then modeled at a level which really takes into account spiking, membrane dynamics, spiking mechanisms, and so on. And really, for instance, ask questions like, does the realistic timescale of how quickly the membrane in actual cortical neurons evolves, about timescale of 10 milliseconds, now how does that affect the capability of keeping activation sustained when the input has been removed? So when then activation only arises by recurrent connectivity in the network. And it might even ask questions like, mechanistic issues like dopamine that could be manipulated in an animal experiment. And how do dopamine levels, for instance, influence the stability or not of sustained activation? So this is, for instance, from work Daniel Dustowitz did. He was actually at the Ruhr-University for a long time in one of Güntergen's lab, and had a junior group there, and is now I think in Darmstadt, if I remember correctly. Or is it Würzburg? I'm confused right now where he is, but in Germany. So this is just an example. So there's a whole continuum of models that go from very reductionist, neurally realistic, to more and more abstract. So for instance, what Laurence Viscos showed you last week were models that were closer to neurophysiology than these psychological connectionist models, where a neuron stands for a ladder. It's not something that you can really observe in the brain, but you can observe neurons that have, for instance, certain receptive fields and tuning curves in the brain. You can always say this in visual cortex area 1. So that you see that there will be sort of intermediate level between this very, very biophysical low level and then the very abstract connectionist. And it's a continuum like that. So I want to talk about levels a little bit. There is a famous classification of levels that goes back to a cognitive scientist called David Marr, who died very early. And so there was one of his claims to fame to have defined these levels. And he talked about 3 levels of description. I personally am a little bit critical of this view, but it's very influential. And I want to go through those very briefly. So he talked about abstract computational principles, algorithmic level, and implementation level, and did this both in AI and in human cognition. So the abstract computational level is meant to have slightly differently, not just this idea that you compute something on a computer with input output. It was more that you find some mathematical law, some computational principle that enables a certain function. So take an example here. You can actually mathematically show that if you have the optic flow that results from an observer that moves through a fixed, rigid environment where nothing moves, that optic flow uniquely determines the ego motion vector of the observer. The ego motion vector of an observer as a rigid body is 6 numbers, 3 translational numbers and 3 rotational numbers. It turns out only 5 of those are determined mathematically. The 5th is some kind of scaling. You could make everything be larger and further away, and you move faster, and then everything would look the same in the image. And then you couldn't tell that. You have to have some knowledge, for instance, how about how large cars really are to really metrically determine the complete vector. The optic flow here are these little vectors where you're essentially tracking the optic flow is the velocity that would occur in the image, the velocity of points in the image that correspond to the same physical point in the world. Right? It's kind of intuitive. If you move through the world, there's some flow on your visual array on your retina, for instance. So this is a mathematical theorem that we can prove. Computer vision experts have, for instance, done that kind of mathematics. And that's just one example. There are a couple of so-called computational laws of vision that are of this nature. It's computation in the sense you say that something is given and then something else is specified by that. You can compute it in principle. It's determined. Even though the complete way to compute it might actually be a complicated computation that maybe it requires solving some implicit equations and so on. So there are laws like that I think I have, I want to mention probabilistic approaches like Bayes networks could be viewed as being at that computational level. So for instance, some very influential models are sometimes called normative models, like optimal estimation, optimal control, optimal observer, for instance. And these would be, again, computational principles where you show that there is an answer to a certain question mathematically. There is an answer. And it might be uniquely determined under some circumstance, might have certain properties of it. It's normative in the sense it can often be framed as an answer that can be characterized by a norm, like a minimum, minimum energy or minimum quadratic error or things like that. So these kind of ideas are very influential, especially these probabilistic ideas are extremely influential, also because they can be implemented. And when we're talking about the algorithmic level, then that will be some kind of intermediate level that shows how that computational principle can be realized. Again, if you show that something is uniquely determined mathematically, doesn't yet mean that you can actually solve the equation. And to solve the equation, you might need an algorithm, and that algorithm can be often framed as something that you write down in principle, but you don't figure out the details in some sense. So for instance, for AI kind of ideas, sometimes pseudocode provided for particular computational principles. And that doesn't yet take care of exactly how you do that. We'll come to that in a moment. But that describes how it's possible in principle to solve the problem. And in human cognition, you could say that these information processing models of ACT-R and so on are at this algorithmic level because they are based on an analysis, a computational analysis of what the task is, and then they provide an approach of how, in principle, you could realize that task, but they delegate to some subroutines, some functions where it's not exactly clear how you would implement those, or let's say there might be multiple ways of how to realize each individual function. For instance, the original example I gave, a real implementation of this computation principle would require you to actually determine the optic flow from, let's say, a movie that you get out of your camera that's mounted in that car. And one possibility, there are multiple ways to do that. And one possibility is, for instance, to find points in two subsequent images in that movie that correspond to each other in the sense coming from the same location in the world. And there are different ways of how that correspondence can be established, for instance, by matching just the luminance pattern or matching some features that you extracted from the images and so on. And there might be mismatches because sometimes you have very little structure and there could be many patches of image that match, and you might have approaches for rejecting mismatches and so on, and that will be sort of the algorithmic level. Now, the implementation level, you see in the AI case, it would be just a more concrete realization of that, and ultimately a numerical realization of that pseudocode that might address questions about how you store, how often you read back from memory and out. And there might be, again, multiple ways to do that, more or less inefficient ways, different programming languages or different frameworks, maybe TensorFlow or something else. In human cognition, the idea would be that all the neural language, the neurophysiology constraints would come from that, would be at that implementation level. So certainly not a notion neuroscientists like very much, that all their work is just implementation of some more abstract theory. And I think that slightly dismissive point can actually be criticized. And you see that in human or animal cognition, there's really more a continuum of levels within that implementation level. As I just hinted, there are different levels within neural mechanistic models that could be chosen. So I personally am critical, I mentioned, of this categorization, even though it's useful to categorize the research, because it might be a question of what it really means to understand human cognition, right? Would that be just ultimately a complete description of all the cognitive competences of humans at the computational level, and then maybe a complete description of the algorithmic principles, how they do that, and then a complete list of all the neuromechanisms for that. It's not clear. It's not clear in part because some of the cognitive performances will not be reproducible. They would be different in every individual from day to day even, because it depends on experience, it depends on the task, it depends on understanding and on the environment and so on. And that would mean it's not all lawful. There's only certain constraints that are lawful that you could understand, like the laws of cognition, like physical laws. There would be laws of cognition. We would more likely call them principles. And other things are not reproducible. They depend on the history. It's just like the Kepler's laws are really laws of motion. But for instance, the distance that the different planets have from the sun, we would say, well, that's just a question of initial condition. When the solar system was formed, it just happened to be that way, and there's nothing lawful about it, which is the current opinion we have about that physical system. And so similarly, there could be things that are not really lawful in cognition that therefore aren't really understandable. And I'm one of those people who think that there's no a priori no a priori level of description at which these laws reside. We have to find out these laws and at which level they can be identified. It's an empirical question. So, for instance, reductionism would just arbitrarily postulate that it's spiking neurons that are the right levels. And these Marr principles would say, well, it's this abstract computational principle that's the right level. And I would argue we have to find out. So I wrote a little paper about that argues this. And I want to just close this survey over the two vague approaches with this little hint in this direction. So, for instance, I mentioned in the first lecture how cognition is based on sensory motor processes. I argued from the fact that it's very often emerges while a system is immersed in environment in closed loop, acts in that environment. I also hinted that there could be internal closed loops between different subfunctions. And this closed loop is something that's very characteristic of sensory motor behavior. And we know that cognition emerges in evolution in animals from sensory motor. Very early in evolution, you have essentially just sensory motor behaviors that become more and more indirect and more complex, and that's then the cognitive part that emerges from that. It actually also emerges in development. If you look at it as a small child, it's primarily a sensory motor machine and acts directly on its percepts, and cognition over experience emerges. It's not obvious immediately, but there's good evidence for that. It goes back to someone called Jean Piaget, who was one of the founders of cognitive psychology, developmental psychology. And even now, for adults and now for humans, cognition can be acted out and is very much at the basis of our acting. It's an exceptional limit case that we just sit there and think. Most of the time we act, even just by speaking, for instance. And therefore, theory has to be consistent with these properties. And that would, for instance, imply that understanding cognition requires understanding these properties of sensory motor systems, namely stability, that you react to changes in a limited way so that you don't overdo it or don't underdo it. That's characteristic of closed loop systems. Those of you who know anything about engineering know that. And so that would argue for a particular level of description where stability resides. And I argue that it's the level of populations in the brain that capture stability. And then this webpage I pointed to earlier gives you some fun stuff to think about. So, but that's just one particular perspective, and the vast majority of work in cognition can be characterized in these different levels. And Connectionism is certainly still very influential, or is actually maybe the most influential theoretical framework currently available. Okay, and that's the end of this second module.